Okay, so ATM is not decidable. We've proven it twice. Now, the next thing I want to show you is that there are even languages that are not recognizable. So recognizable, we know, is a weaker property than just being decidable, than being decidable. Decidable means there's some Turing machine that can take in strings in the language and always accept or reject. Decidable means there's a Turing machine that takes in strings from the language and will accept if the string is in the language, or takes in strings and will accept if the string is in the language, but it doesn't necessarily reject. It could just keep going forever. And so that's a weaker property. And so far, all of the languages that we've seen that were not decidable were certainly recognizable. Remember, ATM is recognizable. How do we prove that ATM was recognizable? I should have a pop quiz right now, but I won't. Question: How did we prove that ATM is recognizable? Yeah.
By building a Turing machine that recognizes it, where all it does is it simulates the Turing machine running on the string that is like.
Right.
And then if it accepts, then it accepts, then it doesn't terminate. If it terminates, it calls it, or rejects it.
Yeah. And what was the name of that Turing machine? It's what?
UTM.
Yeah. So we showed that the language ATM is recognizable by exhibiting a universal Turing machine that can take in a description of any arbitrary Turing machine M and input to that Turing machine W. And what the universal Turing machine does is simulates the behavior of M when M is given input W. If M accepts, then that computation, M's computation, halts, and therefore the simulator halts and can accept. Okay, so definitely the language is recognizable, whether M accepts W. Okay, if the simulation of M shows that M rejects W, then the simulator will not accept. But what happens if the simulation of M goes forever, because M on input W goes forever? The simulator can't stop either. It doesn't have any magic to predict whether M will terminate, whether halt on W. So it's not a decider. That simulator can't be a decider. It's just a recognizer. So ATM is a recognizable language that's not decidable. But I want to now show you that there are some languages that are also not recognizable. So, ATM is recognizable but not decidable. Okay? And now, theorem. There are languages that are not even recognizable. And so they're certainly not decidable. Okay, because in order to be decidable, they have to be recognizable. And what happened to my magic chalk? Oh well. Okay, so the book actually proves this two ways. One is just a existential proof. That is, there exists languages that are not recognizable. And it does it through not a diagonalization, but through a counting type argument, putting languages in correspondence with some number. I'll let you try to look at that proof yourself. But it also does what I think is a more interesting proof, a more informative one, which is the following. Page 8. In order to prove this, it establishes the following. Actually, the following is a theorem. a language L is decidable if and only if L is recognizable. Now, we knew that. In order to be decidable, it has to be recognizable. And the complement of L is recognizable. Recognizable. Okay, so what's the complement of L? Complement of L are all the strings that are not in the language L. L is a language, it's a set of strings over some alphabet, and the complement of L, L bar, is a set of strings that are not in L. L bar equals a set of strings in sigma star that are not in L. Okay? So let's prove this. L is decidable if and only if L is recognizable and L bar is recognizable. Okay? So suppose L is decidable. Whatever, decidable. What does that mean? That means there's some Turing machine, M, okay, which can take in a string that's in sigma star and accept or reject. It will always accept or reject. And what does accept mean? That means that W is in L. Okay? And what does reject mean? It means W is not in L. It's M is a decider. Okay? I'm really resisting a joke here, but anyway. How many people know what joke I'm resisting? Okay, good. Then I don't have to say it. All right. Consider it said. All right. So M is a decider, and whatever input it's given, it will say yes, accept, or reject. All right, so this exists. So now we want to say that L is recognizable and L bar is recognizable. So how do I build a recognizer for L? You know anyone? Any yeah. Say it louder. Yeah, I saw your lips move, so you must be saying the right things. Right. This is a recognizer for M, for L. Okay, M is a recognizer for L. When the input is in L, this accepts. Okay, that makes it a recognizer. What about a recognizer for L bar? Is this a recognizer for L bar? No, it's not a recognizer for L bar. Okay, but what? Yeah. Yeah, if you just switch these, make this a reject, and make this an accept, then if you just switch the outputs, then in comes a W, and if W is in L, it's not in L bar, and so it rejects, which we don't really even care about. But when W comes in and it's an L bar, this machine will end up accepting. So this is a recognizer. So I'll call this now M prime. Actually, M bar would be a better M bar is a recognizer for L bar. So the existence of a decider for L means that there's definitely a recognizer for L, and there's a recognizer for L bar. Okay. But we do need this technical switch here, because literally M is not literally a recognizer for M, a recognizer for L bar, because a recognizer should accept when the string is in that particular language, and that particular language is L bar. Okay, so we just have to switch these two, and then we're fine. Or we could even, on the reject, we could just even take that away, and this would still be a recognizer. All right, let's do the other side of the proof. Okay, so conversely, I hope people recognize this itself is not a full proof of this. This was in one direction. This is an if and only if statement. Okay, so we have to go in two directions. So conversely, if L is recognizable and L bar is recognizable, then we want to show that L is decidable. Okay? So we have to exhibit, so according to this, L is recognizable, so there's some Turing machine here called M, which can take in W, and it will accept if W is contained in L. And there's another Turing machine, maybe I'll call it M bar, and don't be confused, well, let me just change the names of these Turing machines because I don't want you to be confused with that M and M bar. What's another name for a Turing machine? We've never had another name for a Turing machine. I'm really bad with names. Okay, we'll just call it S. S and S bar. W sigma star, and then except if W is contained in L bar. All right? So we have these two Turing machines, and we want to create a Turing machine that can decide L. So what do we do with those? How do we build a Turing machine that can decide L? Yeah?
You make a new Turing machine, and it runs S and S bar both, like one turn on one and one turn on the other, and then sooner or later one of them will accept, and if S accepts, then you accept, if S bar accepts, then you reject.
Right, and the key word here is parallel. Okay, or one, yeah. You might think, okay, maybe this new Turing machine that's going to decide L should just run first S. And if S accepts, then fine. Okay, but if S doesn't accept, then it'll run S bar. But the problem with that is that what if S goes forever? You never know when to stop and to go over to the S bar. Okay, so instead, the idea is you're going to have a new Turing machine which has inside of it both of these Turing machines, and we've talked about how to do that. It's not a subroutine. You don't call it. You actually have to embed it in the rules. The transition functions of the new Turing machine have got to incorporate transition functions of S and S bar. And then this new Turing machine is going to allow S to take one step, and then it's going to allow S bar to take one step, okay? And this new Turing machine, we can give it lots of tapes because we know that that's equivalent to a single tape. So I'll have a tape for S and a tape for S bar just to make things a little simpler. And we didn't go into detail, but the Turing machine can have, that's fine. Each tape has its own read head. So the overall Turing machine, the super Turing machine, if you like, has to have a mechanism that's going to say, okay, take one step here and one step there. But that's easy in terms of transitions. You have your transition labels for S, and then you always go from there to a transition that gives S bar. You're working on rules of S bar and so on, back and forth. So the basic idea is that you take one step in S, and then one step in S bar, and then another step in S, and another step in S bar. Okay? And your input is either in L or it's in L bar, so eventually one of these two is going to terminate. One of these two is going to accept. And so our simulator never gets into the situation where it goes forever. The simulator that is doing these guys in parallel, so here's my super Turing machine M, that's doing these things, that's running S and S bar in parallel, eventually it will terminate, because one or the other of these will terminate, because for any W, either W is an L or W is an L bar. So eventually, one of these two terminates, and then what does its output look like? How do I create the output? And remember, it gets a W contained in. What does its output look like? How do I? Yeah.
Since we're trying to find whether or not it's a part of L bar, right?
No, whether it's part of L.
Oh, whether it's a part of L. So we have our super, Turing machine accept if S accepts. Otherwise, we reject.
Yeah. So its output is if it's S that ends up accepting, M accepts, and if it's S bar that ends up accepting, then M rejects, because again, this is the decider for L. So it should accept if the input is in L, and it should reject if the input is not in L. But we've argued, because we're going one step at a time here, back and forth between S and S bar, that M will always terminate. And certainly it's doing the correct thing in accepting in this condition and rejecting in that condition. And so we've shown that L is now decidable. Okay? So L is decidable if and only if L is recognizable and L bar is recognizable. Okay? So we've got that theorem. Now let's go back and look at ATM. So, okay, this was the end of the proof of, let me give a name for this thing, theorem B. And this was theorem A. Actually, if you look in the book, they have specific numbers, but I don't know what they are. So this was the end of theorem B. Okay, so now we're going to prove theorem A. So let's let L equal ATM. Okay. So we're talking about a language L, which is in fact ATM. What do we know about ATM?
Decidable.
It's what?
Not decidable.
It's not decidable. What else do we know about it?
It is recognizable.
Yeah. So here we have a language L is recognizable and it's not decidable. Okay, so we know two things about it. It is recognizable and it's not decidable. So what can we say about L bar using theorem B?
Not recognizable?
Yeah, L bar must not be recognizable, because a language which is both, where if a language and its complement are both recognizable, then that language is decidable. But here we have a language which is not decidable, and yet it's recognizable, so it must be that the complement is not even recognizable. Okay? And that's it. That's the proof of A. Now, what is the complement of ATM? ATM was the strings in ATM are a pair consisting of a description of a Turing machine and then input. And that pair is in the language ATM if that particular Turing machine accepts that language, accepts that string. And the complement is that Turing machine does not accept that string. Okay? And that's not recognizable. There's no Turing machine which can take in another Turing machine and an input W to that second Turing machine and recognize that that input Turing machine would not accept that input that was being given. And all of these things, that shouldn't be so surprising when you fight your way through all the words and you finally internalize what all these things are saying. It all comes down to this issue that a Turing machine might run forever. And there's simply no other Turing machine that can look at an arbitrary Turing machine on an input and know whether that Turing machine is going to run forever. But we didn't leave it at that level of intuition. We actually constructed rigorous mathematical proofs, which hopefully are clear when you look at them with a clear state of mind. And so all of this is proven. It's not, but the sort of intuitive crux of the problem is, again, this issue of that a Turing machine might run forever if it doesn't accept. It doesn't always have to reject if it doesn't accept. All right, so everybody get this? This is a nice mathematical, clean way of doing things based on this fact. Okay, so now here's an exam question. If a language is decidable, is its complement always decidable?
Yeah.
Yeah, who said yes? Good. Yeah, that's true. At least it seems to me right now. I just thought of the question off the top of my head. We have all the machinery here that should give you that implication. Language is decidable if and only if L is recognizable and L bar is recognizable. Well, so now we say, what about the language L bar? Is it decidable? Well, decidable if and only if L bar is recognizable and L is recognizable, but that's what we just had as a condition for L is decidable. So L, you should be able to do that kind of stuff. And similarly, using theorem B, you should be able to come up with this kind of conclusions as well. And manipulations of that type make wonderful exam questions. Okay, so I'll try to find more of those to ask you. All right, so now we know that there are even languages that are not recognizable, and we even have one in front of us. It's ATM bar, not recognizable. Okay, so I think we finished whatever chapter we were on. Now I'm going to move on to the next chapter. And I want to say something about homeworks. Your last homework was due on Tuesday. Well, you have the extension. And I haven't given you another one because we have not covered enough material yet for new homeworks. We've actually run out of homework problems in the book. So what I have to do in order to give you a new homework set is find homework questions from somewhere else, which can take me a while. But tonight I should have some problems posted for you on this kind of material and on what I'm going to talk about in the next 20 minutes. Okay, so you should have a next homework. It's just that if you look in the book on the chapter that corresponds to what we've been talking about, we've already used up all their questions, so it's kind of unfortunate. I mean, it's really unfortunate because what he's done is, in the first edition, I don't think he had any answered questions. And in the second edition, which is what we're using, he has questions that are answered. So it looks like he took about half or a third of the questions and then provided the answers, which knocks out about a third of the questions. And so there just aren't any good ones left in that chapter. Okay, so the next chapter it's called reducibility or reductions, something like that. Okay, So this, I've actually mentioned reductions before, and I told you the joke about boiling water in a kitchen, and how that illustrates the notion of a reduction. Reductions are really, really important in not only undecidability theory, decidability theory, and in NP completeness, we're going to get to later. So the whole notion of doing reductions is a really central part of theoretical computer science, and the main thing we're going to use reductions for in this chapter is as a way of proving additional problems are undecidable or unrecognizable. Instead of having to go back in each one of the problems that we want to prove is undecidable and do a self-reference proof or do a diagonalization proof, we're going to be able to do simpler proofs. Now that we have a repertoire of some problems, ATM being the principal one, now that we have a repertoire of problems that we know are undecidable, and we have one that's unrecognizable, now we can prove additional problems are undecidable or unrecognizable through this technique called reduction. So a reduction, in sort of abstractly, we're going to reduce language A to language B. What that means is that we're going to use recognizers or deciders for B to be able to recognize or decide the language A. My chalk has disappeared. Okay, language reduce language A, or the language recognition question of A, to the recognition question of language B. That means that, or decider. Let me just do decisions instead of recognition. Okay. So that means you assume that you have a decider for B. In this game of reductions, assume you have a decider for B, or assume that a decider for B exists. Okay, but what you really want, you want a decider for A. And so what is a decider for A? In comes some input W, and out comes accept or reject. Okay? If we can reduce A to B, what it means is that we can use the decider for B to make it turn it into a decider for A. Okay? So use the decider for B to become a decider for A. Okay? For example, simplest example, assume we have a decider for some language L. Okay? And now I want a decider, so this is accept or reject. And now I want a decider for L bar. Okay? On the assumption that there's a decider for L, now I want a decider for L bar. I can reduce the L bar, the problem of having a decider for L bar, to L. How do I do that? Again, what we said, reduction means that you can use a decider for B to become a decider for A, or to create a decider to become by extension, but anyway, to create a decider for A. So if I have a decider for some language L, and in particular the other language that I want, so here A is L bar, and B is L. If I have a decider for L, B, and I want a decider for L bar, which is my A, how do I use this decider to become a decider for A? Yeah.
A decides B bar.
A decides B bar. No, not quite. We did essentially this just 10 minutes ago. We just didn't give it a name. Yeah. Yeah, you just take this decider for B and you put it into another box, and this becomes a reject, and this becomes an accept. Okay, and this big box now is a decider for L bar. Okay, so we've reduced the problem of finding a decider for L bar to the problem of finding a decider for L. Okay, so these two particular languages, L and L bar, illustrate reduction because we already understand how you can turn a decider for L into a decider for L bar just by switching the output. Now, in the general definition, A and B are not necessarily L and L bar. They're just two languages. Okay, but the idea of what a reduction is the same. It may not be easy to find one. In fact, it may not even be possible, depending on what A and B is, or what A and B are. Okay, but the definition of what a reduction is, or how you reduce the problem of deciding A to the problem of deciding B is the same thing. You assume, what it means is that if you had a decider for B, you could create a decider for A. So A reduces to B means that a decider for B can be used to create a decider for A, and just making that a little bit more abstract, if B is decidable, then A is decidable. That's what it means to reduce A to B. So I'll call this a definition. So A reduces to B if B is decidable implies A is decidable. Okay? So, i.e., B decidable implies A decidable. Okay? A reduces to B. This direction of logic, or what it means for one language to reduce to another language, is infinitely confusable. Namely, people get this backwards all the time. When you say A reduces to B, which way does this go? And you just have to always stop. I have to always stop. And it's just like I can't ever remember what 8 times 7 is. I have to think that through each time. And I have to think this through. A reduces to B. What does it mean? if B is decidable, then A is decidable. Okay, that's the direction of the implication. All right, so let's now that we have the definition, let's derive some consequences of the definition. Purely a definition, but consequences. Well, the main one is this. Well, actually, I'll do the minor one first, because we have 5 minutes. So 2 consequences, the minor one and the major one. If actually, no, that's there. That's the minor one. I was just going to repeat that. Okay, we'll do the major consequence. Okay, that's why the minor one is so minor. It's basically in the definition. All right. The major consequence is this. If A is already known to be undecidable, okay, and we also know that A reduces to B, then we should be able to conclude something. What can we conclude?
B is undecidable.
B is undecidable. Okay. If A is already known to be undecidable, and you can also exhibit a way of reducing A to B, that is to use a decider for B, a supposed decider for B, to be a decider for A, to become a decider for A, then you have to conclude that there is no decider for B. Because a decider for B, along with that reduction mechanism, would become a decider for A. But there is no decider for A. We already know that. So there can't be a decider for B. So this is major in terms of its consequences, because we're going to use this as our major tool for proving additional problems are not decidable. But it's not really major in terms of logical thinking. It's just a trivial consequence of these definitions. Okay? So, hopefully that's understandable and clear. And so how we're going to use that, we already know that ATM is undecidable. Okay? So to prove additional problems, or additional languages are not decidable. One of the ways we're going to do that is, let's say, to prove an additional language, call it L, is not decidable, we will exhibit a reduction of 2. Okay? So what goes in this box? What goes in this box? ATM. What goes in this box? L. Right. We know that ATM is not decidable. If we exhibit a reduction of ATM to L, we can then conclude that L is not decidable. That's what this is. Okay? If ATM is known to be undecidable and ATM reduces to L, then L is undecidable. Okay? So that's the game plan, and next time we'll actually do this for a number of additional languages.